Okay. So feel free to interrupt at any time. The prepared content that I have is pretty short, so we'll probably end early. But my plan was to close by stepping back a bit and looking at this whole issue of model-based design and how it's impacted by your choice of languages and how you go about doing the design for safety critical systems. So you probably remember this picture, this audacious picture from one of the early lectures, which pulls together at a very abstract level science, engineering, and mathematics. And I think I wanted to bring this picture up again to talk about where lingua franca particularly fits in with this. So again, just a reminder in case you don't remember what this is about, but at the bottom layer, we have the thing in itself, which is, to use Immanuel Kant's term, your physical system, which in the context of cyber physical systems, this is both the cyber and the physical part. So this is the physical microprocessor interacting with the physical car, for example. A scientific model of that is one where you construct a model where the goal is to make the model behave like the physical thing, or to emulate the properties of the physical thing. And I pointed out that that's complementary to a different use of models, which I call an engineering use of models, where your goal is to construct physical things whose behavior emulates that of models. And so, the classic example that I use for people who are at least somewhat familiar with circuits is digital circuit design, where your engineering model might be a logic diagram, and your goal is to make silicon that emulates the behavior of that logic diagram. The logic diagram is not a scientific model because it's not an attempt to describe the physical thing. It's not incumbent on the logic diagram to behave like the physical thing. If you wanted to build a scientific model of that same piece of silicon, you would probably use diffusion equations, for example, to model the effect of the various fields on the motions of electrons through the silicon, right? That would be a very different kind of model for that piece of silicon. And then above that, we have relationships between models where one model might be an abstraction of another, meaning it's usually simpler, it omits some detail, and conversely, a model may be a refinement of one. And again, the use of abstraction and the use of refinement are kind of complementary. So when you build a lingua franca program, you're actually building a model at a fairly high level in this stack. And then there's a code generator that invokes a refinement process, which creates a new model. Okay, that new model is a C program or a Python program, which is definitely a model. And that may be further refined into another model. So the C program could be compiled into a machine code program, which is again a model. And then you get a physical thing in itself, a microprocessor, your laptop, for example, to execute that program. And then the program is treated as an engineering model because you expect, in fact, demand that your microprocessor execute the program correctly. And the correctness is defined by the model, not by the thing in itself. Okay. So that kind of process where you do this successive refinement until you get down to the physical thing is what's going on at really in any programming exercise. But there's also a very important role for scientific modeling in these. So for example, if you're interested in the question of whether a deadline will be violated in a lingua franca program, There's nothing in the program itself that tells you whether the deadline will be violated. It's just that information isn't there. You need information about the physical realization of the system in order to determine whether the deadline will be violated. And for that purpose, you might use scientific models. So for example, you might have a model of the microprocessor that you're running, and you might do analysis on your program that determines worst case execution times given that model of the microprocessor. And then you could use those worst case execution time estimates to determine whether a deadline violation will occur. Now, the other thing that it's important to understand is that in lingua franca programs are by default deterministic in a certain sense. Okay, and this question of determinism is one that I want to kind of go back to and look at it in a little more detail. But the important thing to understand is that determinism is always a property of a model and never usefully a property of physical things. And the lingua franca program actually includes various escape hatches that allow non-determinism into the behavior. One of them is the deadlines. The behavior of the deadlines is determined by things that are completely outside of the control of the model. And therefore, if you have a program with deadlines and deadline violation handlers, that program has more than one possible correct behavior, because if the deadline violation handler is invoked, it's going to give you a different behavior than if the deadline violation handler is not invoked. And so that determination of whether the deadline violation handler will be invoked is determined more by the physical realization of the system than by the program itself. Okay, is that clear? Okay, so given that picture, what really is a model? Well, very abstractly, a model is any description of a system that is not the thing in itself. Okay. And so that's a very broad definition. Now, when people talk about model-based design, they often think in terms of higher level models like UML models or Simulink models or something like that. But, sometimes people say, well, a program is not a model. A program is, an implementation. Well, that's not true. A program is not a physical thing in itself. Well, I suppose some rendition of the program might be. If you print your program out on a piece of paper, that piece of paper is a thing in itself. And if you use the word program for that piece of paper, well, then you're using the word program to describe a thing in itself. But most of us don't use the word computer program to describe that piece of paper. We use the phrase computer program to describe the code. And we say, for example, that the code on the paper and the code on our screen are the same program, even though they're two different things in themselves. Okay, so in that case, it becomes really very clear that that program is a model, not a thing in itself. So this is a model, okay, and one of the properties of this model is that you can make very definitive statements about it. So in particular, let's look at this program, and let me ask you this question. So this is a C procedure. Does line 8 execute? Any thoughts about that?
I would guess no.
Yeah, it shouldn't, right? Because line 8 should execute only if this variable x is less than 0. It turns out in C, you need to make a few assumptions in order to make that assertion, right? Because C is a very unsafe language, right? This variable x gets passed in on the stack. The stack is not very well protected in C. Some other piece of code that's running in another thread, for example, could write all over your stack and change the value of x, in which case you might find yourself in a situation where x is less than 0. More modern programming languages, by construction, or by definition of the language, disallow those kinds of operations and enable you to actually just read the logic of the individual piece of code that you're working with, and you would then be able to determine that line 8 does not execute. But that property that line 8 does not execute is not a property of any physical realization of this system. It's a property of the model. Okay. Any physical realization of this system, even in a much safer programming language, can't really make any guarantees like that, right? You might have an alpha particle that comes in and flips a bit in memory and causes this variable x to suddenly become negative, at which point line 8 will execute. It's very unlikely, but there's nothing about the thing in itself that makes that incorrect intrinsically, right? The thing in itself behaves the way it behaves in the physical world, irrespective of any notion we might have of correctness. But the correctness of the program is something that we can make definitive statements about, right? So that's a key difference between working with models and working with the actual physical thing. The physical thing will always have properties that are not represented in the model. So for example, if I want to make an assertion that this program is deterministic, I have to make some qualifying assumptions in order to assert that the program is deterministic. Okay. So this is one of my favorite pieces of artwork from Magritte to use in such a context, right? Magritte very cleverly has this painting of a pipe, and here it says in French, "Ceci n'est pas un pipe." This is not a pipe, and it's not. It's a painting. So this is the key essential difference between a model and the thing in itself. Okay, so what are the purposes of models? Well, there's all kinds of different purposes. They could describe the structure, the weight, the dimensions of a system. They could describe energy needs, temperatures. They could describe dynamics. They could specify a design. They could simulate a behavior. They could verify conformance with a requirement. They could specify a requirement. There's just a huge number of possible uses for models, and you use different kinds of models for each of these purposes. Oops. So a few of the properties that we might look for in models. One is the question of whether a model is formal. Formal actually, in a very literal sense, means almost devoid of meaning. It means that the properties are sort of self-contained and self-defined. But in practice, a formal model is one that's given in some well-defined machine-readable syntax that can be mechanistically manipulated using well-defined rules. And you can derive properties of the model from that, from those formal properties, okay? And computer programs almost always fall in this category. They are, in fact, formal models. They have these properties. There's well-defined machine-readable syntax. It can be mechanistically manipulated, and you can derive properties from it in a very systematic way. An executable model is a formal model that describes the dynamic behavior of a system as opposed to some static properties. Okay, and a machine can be used to model, you can use the model to simulate that dynamic behavior. So when a microprocessor executes your program, that's really what it's doing, is it's simulating the behavior of your program. And then a faithful model is one that is that reasonably accurately conforms to the properties of the thing being modeled. And again, this actually is true for both scientific models and engineering models. In the context of engineering models, a good microprocessor is one that correctly executes the programs that you give it. And correctly, in this case, means that its behavior conforms with the formal properties of that programming language, okay? A bad microprocessor would be one that fails to do that, that introduces errors when it executes your program, for example. For a faithful model, for a scientific model, You don't talk about the thing in itself being good or bad. You talk about the model being good or bad. So that's really the key difference. In engineering, it's more incumbent on the thing in itself to match the model. And in scientific models, it's the reverse. It's incumbent on the model to match the physical thing. Okay, so determinism is a property of models. And the property is given some initial state of the system and given the inputs, the model describes exactly one behavior. But you have to be very careful with this definition because you have to define these terms. What do you mean by inputs? What do you mean by behavior? What do you mean by state? Okay. For example, if I give you a lingua franca program and it has a physical action in it, and I define the inputs to be not only whatever values are provided on that physical action or any other source of inputs, but also the timestamps that are assigned to those values, okay? Then I can define behavior in such a way that the program is, in fact, deterministic, okay? And the behavior will be the timestamps and values of all of the outputs and state variables that are calculated by the program. If I define that to be the behavior, then, and I define the inputs to include the time at which physical inputs are provided, the timestamp assigned to those physical inputs, then the program is deterministic. If I don't include in my definition of inputs the time value of the inputs, the timestamp assigned to the inputs, then the program is no longer deterministic, same program, okay? So it really depends on how you define inputs. Similarly, if I include in my notion of behavior how much heat the microprocessor generates, then no lingua franca program is deterministic because there's many possible heat profiles that are consistent with the program. And so the program allows many possible behaviors and consequently would be non-deterministic. So the question of whether a model is deterministic depends entirely on how you define these variables, these terms, state, inputs, and behavior. The value of a deterministic model is that if you have well-defined inputs and it gives you exactly one behavior, the model is much easier to test, okay? Because you can check that the behavior corresponds with what you expect given those inputs, all right? So this issue of testability is really the primary benefit that you get from deterministic models. Now, is the physical world deterministic? Well, this guy thought so. Okay, Pierre-Simon Laplace was doing rather spectacular work as a scientist in the heyday of Newtonian mechanics. And he postulated what is now called Laplace's Demon, where he said very colorfully that that a great intellect that could know the positions and momentums of all of the particles in the universe at an instant in time could predict all of the future and could see all of the past of the universe. Okay, so that great intellect became known as Laplace's Demon, and it sort of embodies the principle, which is kind of a core idea in Newtonian mechanics of a deterministic world governed by relatively simple laws of physics, where given the state of some system, you can project into the future with complete confidence what the behavior is going to be and determine the past with complete confidence. Now, I mean, I'm curious. Maybe we can have a show of hands. How many people think of the Newtonian model of the physical world as in fact being deterministic in this way? Siegfried says no. Okay, yeah. Johannes says no. Yeah, I mean, there's really a number of places where this breaks down. You know, I think the most obvious one is actually a very Newtonian class of behaviors, which I'll get to in a second. But first, I want to point out that there's a really very nice proof by this fellow, David Volpert, who proved that Laplace's demon cannot exist. Okay, I don't think anyone would find this surprising, right? That Laplace's demon could not exist, but to have a fundamental mathematical proof that this demon is impossible is pretty interesting to me. And the basic premise of this proof is that in order for the demon to exist, it would have to exist in the very physical world that it's trying to predict. And this fact that it would have to exist in the world that it's trying to predict creates a kind of self-referentiality that leads to a incompleteness that is similar to Gödel's theorem, Gödel's incompleteness theorem, or the undecidability in Turing machines, both of which arise from a kind of self-referentiality in those systems. And so this is another kind of self-referentiality that leads to an impossibility. And so it's a fascinating observation, I think, very theoretical, of course, but not really that surprising. There's much more practical observations that show that even very classical Newtonian physics is not, in fact, deterministic. And one very simple illustration of this is generally metastable systems. There's a very nice example that's due to a philosopher named John Norton. And this created quite a stir because a lot of physicists were kind of offended that a philosopher was doing this, I think. But Norton really did a very good job with the physics. He constructed a rather simple example where the math really works out in a rather straightforward way of a metastable system. And it consists of a mass that sits on the top of a dome. And he picked a particular shape of the dome, which is given by this formula here. This height is proportional to the distance r along the curve. And you might think that's kind of an odd way to define the dome. And it is. But the reason that he defines the dome this way is that the math works out very simply, right? And he also showed that in fact, many other dome shapes, in fact, most other dome shapes exhibit the same properties. It's just that the math gets a lot more complicated. So the property of interest is that if you position a mass perfectly centered on the top of this dome, okay, and it's perfectly still, it's not moving, and assume that the dome is frictionless, so we don't have to worry about rolling or anything like that, the mass can slide, then Norton showed that without violating any of Newton's laws, that the mass can spontaneously start sliding down the side of the dome at any point in time. And that there's no violation of any of Newton's laws, none of the conservation laws, nothing. And the interesting thing about this is that most people are kind of uncomfortable with this because Newton's laws suggest that motion is always a consequence of a force. But that's not really what Newton's laws say. Okay, Newton's laws give a relationship between this abstract concept of force and motion. But they don't say anything about causation. There's nothing in Newton's laws about force causing anything, okay? And most people are very uncomfortable with this idea of uncaused action. But there's nothing in Newton's laws that prevents this uncaused action. And when I first encountered Norton's argument, I thought for sure he was wrong. That something was wrong here, because how could the ball start moving without any force being applied to it at the time it starts moving? And I finally realized that Norton was right, and that the breakthrough for me was when Norton in his paper points out that in his formulation, there is no time at which the ball starts moving. There is no first time when the ball is moving. There is rather only a last time at which the ball is not moving. Okay, so if at time t the slide starts, it doesn't really start at t, it starts at t plus epsilon for arbitrarily small epsilon. At time t, the force is zero, the acceleration is zero, everything is conformant with Newton's laws, but at all times greater than t, the ball is off center from the top of the dome, and as a consequence, there's a net positive force pushing it down the dome, and it is accelerating. And you can write down the equations. He does this, Norton does this in his paper. I really recommend reading the paper. It's a wonderful read. It's even more fun to read all the commentary that followed it. Various blogs from physicists giving all kinds of arguments about what was wrong with it, and then counter arguments. And there's a lot of give and take. And I've followed as much of it as I've been able to find, and have ultimately concluded that Norton is exactly right, that Newton's laws are actually completely consistent with this kind of non-determinism. So even Newtonian physics admits this possibility. What about quantum mechanics? I mean, many people, when they first study quantum mechanics, they get exposed to it using the Copenhagen interpretation, which is the usual way that it's taught, which interprets the wave function as a probability density function. It's actually a magnitude squared of a probability density function. And it seems to be representing an intrinsic randomness in the world. But there's a very different interpretation. And I love this quote from Stephen Hawking, right? It's kind of colorful, where he says, at first it seemed that these hopes for complete determinism would be dashed by the discovery in the early 20th century that events like the decay of radioactive atoms seemed to take place at random. It was as if God was playing dice, in Einstein's phrase. But science snatched victory from the jaws of defeat by moving the goalposts and redefining what is meant by complete knowledge of the universe. So what Hawking is referring to here is that in Newton's time and in Laplace's time, the state of a particle was its position and momentum. Okay? And quantum mechanics threw that out the window and said, that can't be the state of the particle. In fact, those two quantities are not simultaneously knowable to arbitrary precision. That's the Heisenberg uncertainty principle. So you can't define the state of a particle as being the position and momentum. And it replaced this notion of kind of capturing the state of the particle with a wave function, which is kind of a different description of what this existence of the particle is all about. One of the odd things about the wave function is that unlike any prior notions of state, it's not a measurable quantity. There's no way to measure the wave function of something. And consequently, it actually starts to undermine the very notion of state of a system. So in, I guess, was the 1970s, John Stuart Bell came along and pointed out that in a famous result known as Bell's theorem, which is really quite a simple theorem. And Bell, I'm sure, would have gotten the Nobel Prize for this if he hadn't died before the Nobel Committee finally got around to considering it seriously enough. But and Nobel Prizes are never given posthumously, but Bell's theorem says that if you accept the principles of quantum mechanics, then you have to give up one of two other principles, both of which are very hard for physicists to give up. The first of the two other principles is locality. And locality says that any observation of the properties of an object in physical space cannot instantaneously depend on the properties of another object somewhere else in space. Okay? So you can't have instant action at a distance. That's locality. Then the second property, so you can give up locality and you get a model that's consistent with quantum mechanics, or you can preserve locality, but then you have to give up a second principle, which is even harder for physicists to give up. And it's given a name that makes it especially hard to give up. The property is called reality. And the property reality says that whenever you make an observation of a physical object, that the observation that you make is ultimately determined by the state of that object. So in other words, the object has properties that determine every measurement that you make of that object. Okay? That property they call reality. And Bell showed that if you accept quantum mechanics, you have to give up either reality or locality. And you can see, if you follow in the literature, there's a lot of angst among the physicists about this. And my informal count has come to the conclusion that the majority of physicists seem to have chosen to give up locality. And I have come to the conclusion myself that that's the wrong choice, that the right choice is actually to give up reality. And so it's actually kind of consistent with what we see in computer science with distributed systems, that the very notion of the state of a system is intrinsically problematic. It assumes that, that there's somehow at an instant a set of properties that completely define that object. And it seems that that might not be the case. And certainly in the context of distributed systems in a very practical way, it's not the case. You can't really talk about the state of a distributed system in any meaningful way and use that in any practical way. And as a consequence, for me, it's actually somewhat intuitive that maybe we have to give up this notion of state even at the very core of the physical world. So if you give up that notion of state, then you regain locality, which makes quantum mechanics then consistent with relativity. If you give up locality, then quantum mechanics and relativity are inconsistent with one another. So okay, so the physical world, I think if there isn't even a well-defined notion of state, we can't even talk about whether the physical world is deterministic or not. The question doesn't make any sense, right? If we define determinism as given an initial state and given some inputs, you get one behavior. If I can't give you an initial state, I can't really answer that question about whether a system is deterministic or not. And so I really stick to my guns here that the question of determinism about a physical system is a nonsensical question. We should really only ever ask whether a model is deterministic. So Newton's laws, in certain circumstances, give us deterministic models. So here's a Newton's law description of a behavior of a set of particles. Here's an attempt to construct something that should behave according to Newton's laws and actually does a really, really lousy job. Okay, this is a instance of Newton's cradle that I bought on Amazon for $6, including shipping, and it's a piece of junk. The balls in the middle are supposed to stay still when you get this collision, and it doesn't even come close. So if I try to describe the behavior of this system using simple Newtonian mechanics, it's going to be a real mess. So, and yet our models, the deterministic models, are really useful, right? This deterministic model of software is useful. Instruction set architectures, which also give us deterministic models of underlying electronics. Synchronous digital logic is a deterministic model. These are very useful, even if the physical world is messy. And differential equations are deterministic models, and we use them all the time. It's they're essential to our engineering processes that keep planes in the air and so forth. But as soon as we combine the best deterministic models of the physical world with the best deterministic models of the computational world, we get non-deterministic models. This is, I think, the core intellectual problem in cyber-physical systems today. That the minute you do this combination, you've got a non-deterministic model. And the primary reason is that the two models use completely different approaches to dealing with the notion of time. When we talk about computer programs, we abstract away time. We only talk about sequences of events. And when we then try to align that with some model of the physical world, which may itself be perfectly deterministic, that model typically has a very clean, simple notion of time, the Newtonian time model, right? Where you've got some variable t that advances uniformly everywhere in a continuum. But put these two together, have them interact with one another, and the number of behaviors they describe is not one, but a vast number of behaviors. So in a big picture sense, this is the problem that lingua franca is trying to address. It's trying to bring the notion of time in the program much closer to the notion of time of the physical world. Okay. We're unable today to align them perfectly, but if we bring them closer, we can get closer to deterministic combinations of physical models and computational models. So here is a simulation model of Newton's cradle that doesn't have this messiness, right? This is obviously generated by an artifice, right? A computer program, beautifully rendered with nice shadows and reflections and so forth, but clearly idealized. Okay, whoops. So what is the value of simulation? Well, that's a key question. So I went to a conference in Washington, D.C. 4 or 5 years ago that was organized by an arm of the National Science Foundation that was focused on the problem of the ineffectiveness of simulation systems in the world of robotics. Okay. And the people there were lamenting what they described in this very nice short phrase: simulation is doomed to succeed. The problem that roboticists face is that they build a simulation model of what the robot should do and get the simulation to work perfectly, reliably, works every time. Okay. Then they try to deploy that on a physical system, and the physical system ends up not behaving at all like what their simulation model predicts. So what do you think might be wrong here? Why does this happen? Any thoughts about that from out there?
Well, the model might not be faithful. So it might be too idealistic to adhere to the real world, right?
Yeah, the model might not be faithful. And remember that faithfulness is sort of agnostic to whether we're talking about engineering models or scientific models, right? It could be the model might not be faithful because the model is not good enough, or the model might not be faithful because the robot implementation isn't good enough to match the model, right? Those are two different scenarios. And I think the situation is that the robotics people were not making a distinction between those two scenarios. They were using a model that was really a specification of the desired behavior as if it were a scientific model, and then discovering that it wasn't a very good scientific model. Okay. So to give you a really concrete illustration of how these two things can get confused, I got approached by a large industrial automation company at one point that was trying to improve their virtual prototyping of factory floor systems. Okay, so they wanted simulation models where they could build a prototype of a bunch of robotic machinery doing manufacturing. And they were finding that they were having a very hard time getting the simulations accurate enough. And there were a number of reasons for this, but one of the reasons was that their simulations were not capturing the timing of the software accurately enough. And so they came to me because they knew that I had done some work in the past in this area and said, you know, could we help them improve the accuracy of their modeling of the timing of the execution of the software? And I said to them, no, I can't help them do that. And I also said that I didn't think that was the right thing to do either. That their goal was to create better scientific models of what the microprocessors did when they executed the software. And I suggested to them that a more productive approach would be to figure out how to make the microprocessors emulate the behavior that the software specifies. If the software explicitly tells you what the timing should be, and then you can get the microprocessor to match that timing, then your models are going to be, in fact, accurate by construction. So it's the question of whether you're trying to improve your scientific modeling or improve your engineering processes, right? It's this bidirectional thing. And I see lingua franca is very much about this second approach, right? It's about writing the programs in such a way that they specify timing behavior. And then your goal is to try to get the microprocessor to match that timing behavior as closely as you possibly can. Make the system match the model rather than the other way around. Okay. And, you know, we're not completely there right now. So for example, one of the things that we're sort of stuck with is today's microprocessors. And they're not designed with this objective in mind. One of the other projects that we have in my group has been focused on trying to fix that problem and to show that you can in fact design microprocessors where you can in fact specify timing behavior very precisely, and then have the microprocessor actually deliver that timing behavior very precisely. Today, if we're using, you know, commodity off-the-shelf microprocessors, the timing accuracy that we can get from them is rather coarse. But in principle, it should be possible to get much more precise timing accuracy. I think, you know, the underlying silicon is certainly capable of it. It's capable of very repeatable, predictable timing at nanosecond scales. So if we just design the microprocessor architectures to give us control over that timing, then we get a very different story. Okay, so this is really about what kind of modeling we're doing. And so the argument is that this is really confusing engineering and scientific model. So there's another use of simulation that I think illustrates this point rather nicely. This is work done by my colleague at Berkeley, Sanjit Seshia, and his group. One of the problems that people face in the self-driving car world is that they're trying to train AIs, and they need data to train the AIs. And they want the AIs to be able to handle emergency situations that are extremely rare in the field. Okay, very odd situations that can occur. And the problem is that if the data that they're using to train the AIs is all real world data, then these rare situations are going to be very rare in the data. In fact, many of them will just be non-existent. You can't collect enough data to have all of the really weird idiosyncratic situations come up. You know, simple things like badly parked cars, right? Or, you know, any sort of odd situation, right? And so one of the things that Sanjit Seshia and his group have been doing is they've been using formal methods to construct scenarios that are kind of extreme cases of odd situations. So think of it as a whole space of possible situations. They're looking for the sort of the Pareto optimal odd situations. Then they generate simulation data for those odd situations, and then they use that simulation data to train the AIs. And the hope is that they will be able to use this in order to get the training sets to actually include a large enough number of really peculiar situations in order to be able to have the cars be a lot safer when they actually do encounter these odd situations in the physical world then. So, okay, the reality is that engineers often confuse the model with the thing being modeled. And I think Solomon Wolf-Golomb had a really nice way of expressing this, which is, he pointed out, you will never strike oil by drilling through the map. But we confuse the map and the territory all the time. Whenever we talk about a computer program as being an implementation, for example, we're confusing the map and the territory. This does not in any way diminish the value of a map. So if you remember, I think I told you this story that I heard from an engineer who had worked on the Boeing 777, where he told me that that when Boeing started making this aircraft in the mid 1990s, that they stockpiled the microprocessors that they expected to use for an entire 50-year production run of the aircraft. And the reason for that is that they kind of needed to freeze the design, right? They needed to be able to use exactly the same microprocessors 50 years later, because if they changed the microprocessor, even though any microprocessor would correctly execute the C code, it wouldn't give you the same behavior. And so the problem here is once again one of confusing the model and the map and the territory. In essence, the design of the 777 isn't an abstract model at all. It's a physical realization. And consequently, you need the physical realization to be the same for each instance. So if you think of the way we use abstraction layers, right? So here's a sort of involved picture, but the picture has a somewhat formal structure. So each box here, so for example, this box at the bottom represents a set of objects, which are either models or physical systems. Okay, so in this case, I guess actually in this case, all of the things shown here are models, right? So this is microprocessors. So for example, one member of this set is a particular microprocessor design, all right? There would be many physical instances of that, but just one design, okay? And this happens to be an x86 microprocessor. And consequently, associated with that one object, there's another whole set of designs, which is the set of all x86 programs. There's a particular program that's a member of that set that happens to be a Java virtual machine. Okay, that has associated with it a whole nother set of designs, which is the set of all Java bytecode programs. A particular point in that set is the output of a Java compiler, which produces the bytecode. Okay, but associated with that is the set of all Java programs, which is again another set. All right, and then you can have higher level abstractions of that, such as the set of all Linux processes and so on up the way. Okay, so this layering of abstractions is extremely valuable. Right? The purpose of each layer is to hide the details of the implementation below and to provide a platform for the design from above. So for example, if you're writing a Java compiler, you just need to know about these two layers. You don't need to know anything more, really. Okay? So you get this insulation. The problem with the Boeing 777 is that there was no insulation. Okay. All the layers get jumbled together, and the design actually is the implementation, and every detail of the implementation of the microprocessor becomes important. In fact, when Boeing bought the microprocessors, it went to the microprocessor manufacturer and said, we want them all to come off the same production line. We want them to come from the same mask set. We want them to come out of the production line all within the same few days, okay, so that there's no changes in the manufacturing. They really wanted to be as sure as they could that there was going to be no variability or as little variability as possible between the actual implementation of these microprocessors. And that's what they've done essentially, is they've found themselves in a situation where all of the brilliant abstractions that computer scientists have developed over the last 50 years failed them. None of these abstractions are of any use because it's not enough to correctly execute those programs. You have to actually correctly execute them in this particular way that this particular instance of the microprocessor executes them. Okay, so everything about the design down to the wire lengths of the microprocessor chips gets frozen at the time of the design. So notice that this is distinctly in contrast to this analysis that we can do on programs as models, right? Where we can come to a very definitive conclusion that line 8 does not execute as long as this program is correctly executed. We have a very clear notion of correctness, and we have a very clear way of defining what an incorrect behavior is. And we can develop an absolute confidence in the model, okay? And what we mean by that is really that only a hardware failure is an excuse for this to not conform with the behavior that we've defined, all right? So the key thing to notice here is that this gives a semantic notion of correctness, but always allowing for the possibility of faults, right? So in the context of lingua franca programs, deadline violation handlers are fault handlers. They're an escape clause. They're a way to get out of the execution of the lingua franca program when some of your assumptions have been violated, okay? We treat this as a fault handler, and having fault handlers is an essential part of safety critical design. But you want to make a distinction between faults and normal behavior of a program. And ideally, you want a framework in which you can detect the presence of faults. Okay, so the problem here is that this program doesn't say anything at all about timing. And consequently, if you actually had a deadline on some invocation of something, well, that's not expressed here anywhere. The underlying hardware is very good at timing. okay? But we're kind of stuck not being able to use that effectively because of the software layers above it, right? And so that's a big part of what lingua franca is trying to fix. Okay, let's talk about the terms verification and validation. Okay, so again, here's our picture. So validation is used in a variety of different ways by different people, but if we look at the way it's used by one of the, sort of creators of the software engineering discipline, Barry Boehm, he described validation as the question of whether I'm building the right product. Okay. And this is, the process of this relationship between the thing and the model. And there's various aspects where, the validation question here is really about whether this is the right product. And Boehm made the distinction between that and a very different question, which is the question of, am I building the product right? Okay. And that second question, that verification question, is always about a relationship between models. It's anytime someone talks to you about formal verification, they're always talking about a relationship between models. So unfortunately, you see many people sort of confuse the map and the territory here again. They say, well, this system has been verified and proven safe. And they're implying that the physical realization has been proven safe, which is never true. You can't prove a physical realization safe. You can prove a model safe where you've got a good formal definition of what safety is. So that's a relationship between models, your formal definition of safety and the model that you're proving safe. Okay. So formal verification is always about a relationship between models and never about a relationship between models and things. So I'll close with just some pointers to some papers and books. Some of these go into these kinds of issues at much more philosophical levels, like these two books at the lower right. So some of them are a lot more technical, but so stop there and open up for discussion and questions.